Welcome to Science Pills. Usually when we talk about digging into history, we're talking about, tangible things like you dig up bones or you uncover ruined cities.
Right, yeah, like finding a shard of Roman pottery.
Exactly. You can hold that pottery in your hand and say, definitively, people lived here. And it's comforting because the evidence is something you can actually see and touch.
Yeah, it's a very human way to understand origin stories. We look for physical leftovers.
But when you step into the world of particle physics, that entire archaeological framework just completely inverts.
Oh, absolutely. We aren't looking for pottery. I mean, we are trying to reconstruct a 13.8 billion-year-old explosion, the Big Bang, from the microscopic shrapnel it left behind.
Right, and the ruins we're examining are entirely invisible. We are essentially trying to read the universe's original source code by smashing the hardware together to see what falls out.
That is a great way to put it. And time is currently running out to gather that data.
It really is. The Large Hadron Collider at CERN, the LHC, is in the final stretch of its third operational run, and the stakes are just monumental.
Huge stakes, yeah.
So for this deep dive, we're pulling from a massive stack of sources today. We've got official CERN accelerator reports, technical updates from the CERN Courier, press releases from the Science Media Center, and Ukraine.
Plus the direct data from the four main LHC experiments, right?
Yeah.
Atlas, CMS, ALICE, and LHCb.
Yep, all of them. And we threw in a few foundational texts on cosmology just to, tie it all together.
Yeah.
Because our mission for you today, our listener, is to explore what we are calling existential science.
Existential science, I like that.
We're going to look at the ticking clock of this 2026 LHC run. We're going to unpack the discovery of a brand new particle, which is essentially an ultra-heavy proton.
That one is fascinating.
But most importantly, we are going to explore the ultimate mystery. Like, why our universe is made of matter and why you or anyone else even exist at all. I've got a resident expert here to guide us through this.
Thanks. Yeah, the gap between what happens in a 27-kilometer underground ring in Switzerland and why you exist is actually much smaller than people think.
So let's start with the urgency of right now. The clock is loudly ticking on the LHC. Run 3 officially ends on June 29th, 2026.
Right, and after that, the entire machine goes quiet.
Exactly, for a massive 4-year upgrade period called Long Shutdown 3, or LS3. So this 2026 sprint is short, but the schedule is wildly intense.
Well, it's unprecedented. They restarted the machine with just like 4 bunches of protons circulating per beam, and they've been methodically ramping that up to over 2,400 bunches.
Which is just packing as many protons into the ring as physically possible.
Yeah, and they're also running specialized tests. There's this 2-day low-energy run at 1.2 tau, specifically for the SMOG system.
The SMOG system, right. That's where they inject gas into the beam pipe to study how cosmic rays produce antiprotons in deep space.
Exactly. And then right at the end of the run, they're going to push 40% more protons into the bunches just to completely stress test the equipment.
They're essentially redlining the most complex machine ever built by humans.
Yeah, they really are.
And the reason they're pushing the hardware to the absolute breaking point before this shutdown is to gather enough statistical weight to solve one glaring, almost embarrassing problem in physics, which is the matter-antimatter asymmetry.
It is the elephant in the room of modern cosmology.
Right, because the Big Bang should have created equal amounts of matter and antimatter, a perfect 50-50 split. But, if a particle of matter and a particle of antimatter touch, they annihilate instantly.
They just leave behind nothing but pure energy, poof.
So, if the universe had maintained that perfect mathematical symmetry, it would currently be nothing but a cold sea of leftover photons.
Yeah, there would be no stars, no planets, no biology.
But obviously we are here, and the sources note that about 1 particle of matter per billion managed to survive that early annihilation.
Just 1 in a billion.
Okay, let's unpack this for your listening. If you spin a bunch of coins on a table, half should land heads and half should land tails. That's your 50-50 matter to antimatter split.
Right.
But if a special marble rolls through while they are spinning and knocks a tiny fraction of them to land heads up, the balance is broken. What we are looking for at CERN is that marble. Like, what broke the balance?
And physicists actually have a highly specific framework for finding that marble. Back in 1967, Andrei Sakharov proposed 3 necessary conditions that the universe had to meet to create this imbalance.
Right, baryogenesis.
Exactly, the Sakharov conditions. So number 1 is baryon number violation.
Which means the total amount of matter in the universe has to be able to change, right? Rather than just being a permanently fixed number.
Yeah, exactly. Then number 2 is C and CP symmetry violation.
And this means the fundamental laws of physics have to actually treat matter and antimatter differently. They can't just be perfect mirror images of each other.
Right, there has to be a preference. And then number 3 is interactions out of thermal equilibrium.
So all of this rule breaking had to happen while the universe was rapidly expanding and cooling, so the reactions couldn't just run in reverse and undo the whole imbalance.
You nailed it. And what's fascinating here is that the entire 2026 LHC run is essentially a massive, coordinated hunt for experimental evidence of those exact 3 conditions.
And the search for that second condition, the CP symmetry violation, is heavily focused on the LHCb experiment right now.
Yeah, LHCb is really where we are seeing the breakthroughs. They just found evidence of this symmetry violation in baryons.
And just for a quick reminder for the listener, baryons are particles made of 3 quarks. Protons and neutrons are baryons. This is the stuff that actually makes up you, me, and the stars.
Right. Finding asymmetry in mesons, which are just 2 quark particles that happened decades ago, but finding it in the actual building blocks of the visible universe is the real prize.
So what did the LHCb collaboration actually do?
Well, they analyzed the decay of something called the bottom lambda baryon. They basically counted the decay rates between it and its antimatter partner, looking for any kind of discrepancy.
And they found one.
They did, a 3.2 standard deviation asymmetry. The matter version and the antimatter version simply do not decay at the same rate.
That is a massive clue. But it's not even the biggest news out of LHCb, is it?
Not even close.
Because just recently, on March 17, 2026, they announced the discovery of a brand new particle, the GCC+.
The doubly charmed baryon.
Which, I mean, that sounds like a magic spell.
It really does.
But it just means it has 2 heavy charm quarks and 1 light down quark.
Yeah.
And it weighs in at about 3,620 mammy squared. Now, throwing that number out there doesn't mean much on its own, but it's 4 times heavier than a normal proton.
Which is huge. Finding it proves that the strong nuclear force can bind 2 heavy quarks together, which physicists honestly weren't entirely sure was physically stable.
And they found it with a 7 sigma significance.
Yeah, a 7 sigma result is wild. In physics, a 5 sigma result is a guaranteed discovery. A 7 sigma result is like planting a permanent flag on the moon.
Wow. And didn't this resolve an old mystery from Fermilab too?
It did. A 20-year-old mystery from the CELEX experiment there. They thought they saw something similar, but they just couldn't prove it.
And getting a 7 sigma signal for something this rare is just an incredible engineering feat.
Oh, absolutely. It relies heavily on upgrades LHCb installed back in 2023. Specifically, the VLO system, the vertex locator.
That's the silicon pixel detector, right?
Yeah, and it sits just 5 millimeters from the beamline, 5 millimeters from the most violent particle collisions on Earth.
That silicon is bathing in a radiation field that would instantly fry any normal electronics.
Exactly. And they combine that with the RICH system, which identifies particles by measuring Cherenkov light.
Which is so cool. Cherenkov light is essentially a sonic boom, but for light.
Yeah, it's a great analogy.
When a particle travels faster than the speed of light through a specific gas inside the detector, it gives off a literal cone of light. By measuring the angle of that cone, they figure out exactly what kind of particle just flew by.
It's genius engineering. But if we connect this to the bigger picture, we need to look at what these discoveries actually mean for our existential question.
Okay, wait, I want to push back on the celebration a bit.
Yeah.
We found this heavy proton, the CC+, and we have a 3.2 sigma asymmetry in how normal baryons decay. So, have we solved the mystery? Can we pack up and go home?
I wish, not at all.
Because we found Sakharov's second condition, right? Is the current rulebook, the standard model of physics, complete now?
Nope. The standard model actually predicts the CP violation we just found. The math totally allows for it. But when you run the numbers, the amount of asymmetry we are seeing in these decays is off by several orders of magnitude.
So it's not enough.
Exactly. It is quantitatively far too small to explain why an entire universe of matter survived the Big Bang. Finding this asymmetry confirms our theories are on the right track, but its tiny size proves definitively that our current rulebook is missing a massive chapter.
So if decaying particles in a vacuum can't account for all the missing antimatter, we have to stop looking at isolated particles. We have to start looking at the fabric of the early universe itself.
Right. We have to look at the actual primordial soup of the Big Bang.
Which brings us to the CMS and ALICE experiments.
Yes. So CMS has been studying what they call minimum bias events. These are basically the lowest energy, most common collisions at the LHC.
And usually when you smash protons together, the rules dictate that the debris sprays out in highly focused jets.
Yeah, quantum chromodynamics makes it very directional. But CMS found that in these low-energy events, the debris is highly isotropic, meaning it sprays out in near-perfect spheres.
And the sources suggest this spherical spray points to the existence of instantons, which instantons are essentially fluctuations in the vacuum of space-time itself,
Exactly, they're topological flaws.
like a wrinkle in the carpet of the universe.
That's a perfect way to visualize it. And the crazy thing is, instantons can actually violate baryon and lepton numbers.
Which hits Sakharov's very first condition.
Boom. Exactly. Instantons provide a mechanism for turning quarks into leptons and vice versa. It's a completely different way to cheat the universe's accounting system and create more matter than antimatter.
But analyzing these spherical sprays requires an almost incomprehensible amount of computing power, right? CMS isn't just looking at the spray, they're measuring quantum entanglement between top quarks traveling at high speeds.
Yeah, they are testing Einstein's spooky action at a distance at the most extreme energy scales ever probed.
And to find these instantons and map these entangled states, CMS is processing 40 million collisions every single second.
It's mind-boggling. Human brains and even traditional handcrafted computer algorithms fundamentally cannot handle that.
Right, because when a collision creates thousands of secondary particles, a human-written if-then rule breaks down. The overlapping trajectories just look like a tangled ball of yarn.
Which is exactly why CMS is relying on machine learning particle flow algorithms running on massive GPU clusters to fully reconstruct these events.
So AI isn't just a tool here.
No, it is fundamentally altering the scientific method in high-energy physics. Machine learning looks at the entire tangled ball of yarn simultaneously and just recognizes the pattern.
That's wild. Now, while CMS is looking at the vacuum, the ALICE experiment is looking at the soup.
Right, ALICE does heavy ion collisions.
They've been smashing lead ions together at 5.36 TeV to recreate the quark-gluon plasma, the QGP. This is the liquid that filled the universe for the first millionths of a second.
And they've even been smashing neon nuclei together, which is wild because neon nuclei aren't spherical.
Right, they look like bowling pins.
Yeah, and the shape is crucial. If two of these bowling pin nuclei hit head-on versus side to side, the resulting splash of primordial plasma expands in an asymmetrical oval rather than a perfect circle.
And by measuring the shape of that oval splash, physicists can measure the viscosity and flow of the Big Bang itself. But here's where it gets really interesting. ALICE isn't just smashing these nuclei and watching the pieces fly. The sources say they are measuring the wakes left by individual particles traveling through this near-perfect liquid plasma.
It's exactly like measuring the wake of a speedboat.
Right, just like a boat's wake is wider and slower in thick mud than it is in pure water, the angle of the particle jets shooting through the plasma tells us exactly how dense the universe was a microsecond after the Big Bang.
And understanding that primordial fluid ties directly into Sakharov's third condition.
A departure from thermal equilibrium.
Right. We need to know exactly how the universe cooled down. And we can't talk about the universe cooling down without talking about this ATLAS experiment and the Higgs boson.
Oh, definitely. ATLAS recently found rare evidence of the Higgs decaying into muons at a 3.4 sigma significance.
Yeah, and understanding the Higgs mechanism alongside the quark-gluon plasma Alice is studying helps explain how particles gain mass out of thermal equilibrium as the universe expanded and cooled.
So LHCb is looking at decay asymmetry, CMS is looking at vacuum flaws, ALICE is measuring the primordial soup, and ATLAS is mapping the mass-giving field.
They are all attacking the exact same existential puzzle from completely different angles.
But run 3 is going to end. And even with all this brilliant data, we have essentially exhausted what the current iteration of the LHC can tell us. We just need more collisions.
Which points us toward the horizon.
Right. After the June 2026 shutdown, the machine undergoes a massive transformation into the high-luminosity LHC, the HL-LHC, slated for 2030.
They are swapping out magnets and installing new hardware like crab cavities.
I love that name, crab cavities. They essentially tilt the proton bunches sideways right before they cross paths. Right?
Yeah, so instead of colliding head-on like two arrows, they collide broadside. It massively increases the chance of a hit.
And that tilt is going to deliver 5 times more collisions. To put that in perspective, the HL-LHC is projected to produce 380 million Higgs bosons.
With 380 million Higgs bosons, you aren't just looking at the particle anymore. You finally have enough statistical data to measure how the Higgs interacts with itself.
The Higgs self-coupling.
Exactly.
Right.
This is represented by the symbol lambda-3. We need to map the exact shape of the Higgs potential. The sources describe this mathematical shape as a Mexican hat.
Like a sombrero.
Right. Imagine a graph shaped like a sombrero. Right at the Big Bang, the universe was perfectly symmetrical, sitting at the peak, the very top of the hat.
Okay.
As it cooled, the universe rolled down into the brim, breaking the symmetry and giving particles mass.
So the billion-dollar question is, was that roll into the brim a smooth transition, or was there a bump it had to hop over?
A bump means there was a strong first-order phase transition. Think of it like water boiling. If water boils, you get distinct bubbles of steam surrounded by liquid.
Oh, I see.
If the early universe boiled over a bump in the Mexican hat, it means bubbles of the new vacuum expanded into the old vacuum. The chaotic walls of those expanding bubbles could have provided the exact out-of-equilibrium environment needed for the matter-antimatter asymmetry to lock into place.
So the shape of a mathematical hat literally dictates whether everything we know has a reason to exist.
Pretty much, yeah.
But even mapping the sombrero isn't the final step. The CERN Courier notes that the physics community is heavily focused on the Future Circular Collider, the FCC.
Oh, the FCC is wild.
It's a proposed 91-kilometer tunnel that would absolutely dwarf the current 27-kilometer LHC. It would push collision energies to 100 TeV, which is 7 times what we could do now.
It's the ultimate machine for the late 21st century. It's designed to probe the massive energy scales where grand unified theories and the true origins of CP violation are likely hiding.
But building a 91-kilometer tunnel isn't cheap.
Yeah.
The sources highlight a fascinating detail here. Private donors, like tech entrepreneurs and philanthropic foundations, just pledged 860 million euros, which is about $1 billion to support the FCC.
It's a huge pledge.
And I look at that number and have to ask, why are private citizens dropping $1 billion on a particle collider? Is it just philanthropy for abstract math?
It's actually a massive societal endearment. It goes back to the value of moonshot science. I mean, it's easy to look at the FCC and think it's just about esoteric invisible particles, but look at the technologies required just to make these colliders function.
Right, the computing power alone.
Exactly. The advanced machine learning algorithm CMS uses to sort those 40 million collisions a second directly pushes the boundaries of global AI architecture. The cryogenics, the vacuum systems, the superconducting magnets, they all require completely new materials engineering.
And you think about that Velo silicon detector from LHCb we talked about, the one sitting 5 millimeters from the destructive beam. The custom silicon chips, designed to survive that exact radiation environment, have direct applications in creating next-generation medical imaging sensors. So when you push the boundaries of physics, you force engineering, computing, and medicine to level up with you.
That is exactly why private citizens are investing $1 billion. It's a return on investment that profoundly changes society long before we ever figure out the math of the Big Bang.
So what does this all mean for you, listening right now? It means that a 27-kilometer ring underground in Geneva isn't just a physics lab. It is a cosmological time machine.
Yeah, it really is.
By studying the decay of heavy baryons, by tracking the wakes in a primordial plasma, and by mapping the shape of the Higgs field, thousands of scientists are defending your very right to exist. It means the next time you look in the mirror, you're looking at the ultimate survivor matter that mathematically shouldn't be here, but against all odds is.
It forces a completely different perspective on your daily life. But I actually want to leave the listener with one final mind-bending concept from the sources that challenges our assumptions even further.
Oh, wait, really? Lay it on us.
So, while the main LHC ring is smashing protons, CERN's antimatter factory is running an experiment called GBR.
Okay.
They are currently trapping antihydrogen and cooling it to microkelvin temperatures, like almost absolute zero, and then they drop it.
They drop antimatter, like literally to see how it falls.
Yeah, they are letting it fall 20 centimeters to test how antimatter reacts to Earth's gravity.
Wow.
Because gravity is overwhelmingly weak compared to electromagnetism, trying to measure the gravitational pull on a single antiproton is like trying to hear a whisper next to a jet engine. That's why they have to cool it so much.
Right, that makes sense.
We all inherently assume that antimatter, because it has mass, falls down. But we have never actually seen it happen. What if the data reveals that antimatter falls up?
Wait, if antimatter experiences anti-gravity, that completely breaks our understanding of general relativity.
Exactly. It would rewrite every physics textbook on the planet.
It would fundamentally change our understanding of space-time itself.
Oh, completely. So as we close in on the final laps of this 2026 run, Just remember that the universe still has plenty of foundational secrets left to tell.
It's the ultimate archaeological dig, and we're just hitting the really good layers. Keep wondering, keep asking questions, and we'll catch you next time on The Deep Dive.